A 1,000 kilogram satellite is in a circular orbit that is 160 kilometers above the Earth's surface. The radius of the Earth is 6.4 times 10 to the 6 meters, and the Earth's mass is 6 times 10 to the 24 kilograms. What is the gravitational, kinetic, and mechanical energy of the satellite? So, the gravitational potential energy is given by the negative of the gravitational constant times the product of the two masses divided by the distance. And that is basically the formula for the gravitational potential energy. But in our case, we still have the gravitational constant. M1, let's call this capital M. That's going to be the mass of the Earth. So the mass of the Earth is going to be 6 times 10 to the 24 kilograms. And I'm going to call the mass of the satellite little m. And the distance, remember this distance is from the center of the Earth to the satellite that is orbiting it. So if I draw like sort of circular orbit, d is the distance from the satellite to the center of the Earth. So that includes the radius of the Earth and the height that the satellite is orbiting above the Earth. So our distance away from the center of the Earth will be the Earth radius plus the height that the satellite is orbiting above the Earth. Now, I'm just going to plug all of this in. G is 6.67 times 10 to the negative 11th power times the Earth mass of 6 times 10 to the 24 kilograms times the satellite mass of 1,000 kilograms divided by the radius of the Earth is 6.4 times 10 to the 6 meters and times the height, which is 160 kilometers. I'm going to convert 160 kilometers to meters, and that is 160,000 meters, or 1.6 times 10 to the 5 meters. So that is going to be our value here, 1.6 times 10 to the 5 to 10 to the 5th power meters. And now all we need to do is plug this into a calculator and solve. So this gives you about minus 6.1 times 10 to the 10th power joules. And that is going to be the gravitational potential energy. So I'm going to rewrite it up there. So the gravitational potential energy is minus 6.1 times 10 to the 10 joules. So that's the first part. Now it asks us for the kinetic energy. So if you remember, the kinetic energy is equal to minus 1/2 times the gravitational potential energy. And this simply stems from a satellite being in circular motion. So if we have this as the Earth and like some satellite undergoing circular motion here. Actually, I'm going to draw this a little bit bigger. So if we have something like the Earth and a satellite undergoing a circular orbit, pretend that's circular, you're going to have a centripetal force, which is actually the force of gravity acting on it. So the centripetal force is equal to the mass times the centripetal acceleration, which is v squared over r. And then that, you can set that equal to the force of gravity, which is the gravitational constant, times m1 times m2 over d squared. So it kind of stems from this relationship here. And like the masses cancel and you get like v squared over r equals this quantity here. And we're assuming these two quantities to be almost the same. So this is basically how kinetic energy is derived. And then from there, you can solve for v in v squared over r. plug it into the kinetic, into the equation for kinetic energy, and then you can actually find out this right over here. So that's just how you would derive it, but we're actually just solving this problem here. So this becomes minus 1/2 times the quantity we calculated earlier, which is minus 6.1 times 10 to the 10 joules. And this gives you about 3.1 times 10 to the 10 joules. And the negatives cancel, so the kinetic energy is positive. Kinetic energy is equal to 3.1 times 10 to the 10 joules. Okay, and now it asks us for the mechanical energy. So the mechanical energy is basically the total energy from both the kinetic and potential energies. So the mechanical energy is equal to the kinetic energy plus the gravitational potential energy. Might be better if I say the gravitational energy plus, or gravitational potential energy plus the kinetic energy. This is because the kinetic energy is equal to minus 1/2 of the potential energy. So we can substitute this in, say that it is equal to the gravitational potential energy minus 1/2 of the gravitational potential energy, which is simply 1/2 of the gravitational potential energy. And if you remember, our kinetic energy, which was minus 1/2 of the gravitational potential energy, was 3.1 times 10 to the 10 joules. So we're just flipping the sign, inverting the sign, since that's the only difference. Mechanical energy is going to be equal to 3.1 times 10 to the 10 joules. And we just inverted the sign. You can also plug this back in for that. So the total mechanical energy is equal to minus 3.1 times 10 to the 10 joules. And that is how you would solve this problem here.